best case, if I can get an 80.
Yeah.
Oh, God.
Hey, Dr. Trent, I was wondering for the final project.
Yep.
I know there's like more work if you're taking the class for grad credit.
Yep.
Doing like, let's say I decided like I cannot figure out the project, so I don't want to do the finite volume method. Can I just tell you, okay, I'm not going to do this part. I don't want grad credit anymore. Like, how does that work?
There's a form you have to there's a form we signed at the beginning.
Yeah.
You would have to ask advising
Okay.
if that's the case, because it's because they might have it on file of you kind of signing that, of both of us kind of signing that form.
Yeah.
And so I mean, for me, I'm okay with it, but
Okay.
you know, I just want to make sure that it doesn't go down as that or not.
Yeah, I know when I talked to Dr. Weiss, she said like basically at the end of the semester you sign off on the paper again. So
Oh, okay,
like,
okay.
you did complete it or you didn't.
Okay,
Like,
okay.
So
That's right. That's right.
okay, yeah. So
Okay, yeah, then yeah, that's fine. I'm fine
okay.
with it.
Just asking, just in case I'm like Chris and kind of like have a panic attack and like I can't do this. So
Sure, sure.
Just a random video of someone in a dog, but doesn't that look exactly like me?
Behind you.
Yeah, right.
Yeah, I see that.
I like saw it and looked at the fact that Dr. Trent actually said I'll forget.
Here on, are we just gonna keep covering lessons, or will there be days where we can just work on the project?
Yeah, we'll talk about that today. But we have one lesson after this. This one, which is unsteady schemes and finite volumes, and then that wraps up all the content of the class. And so we're probably going to start it today and probably finish it up next, maybe on Monday, but Wednesday. And then after that, we're just gonna have project time.
Okay.
I think it works out well because last year I couldn't do this just because you know it was still virtual.
Yeah.
But now that we're in person, it's a lot easier for me to kind of go around and kind of help people with the programming. And so I want at the very least the last week, and then maybe a little bit of next week to cover that as well.
Sounds good. That'd be optimal. Because I know I was planning on working on the project after finals week and just dedicate that whole week to it.
Oh yeah, I think most people haven't started it just because you know we had the midterm on Monday, and I know you guys have other stuff going on too. So because I've learned over the last couple semesters that if I don't have class time for it, then it comes into office hours, and you know.
Yeah, that's true.
Yeah, because I want to check and see how everyone's doing, and so I think class time is the best time for that because it's the only time we're all kind of together. Yeah, it's typical. Yeah.
There's just not enough time. There's some senior design, and everything, like literally not time today.
Mhm.
Question on there, that's like, if you could do your undergrad again, what would you do differently? If I not failed my classes the first time. I should not do it.
Any plans for the weekend?
Continue to rest my back.
Yeah. How's that doing? How's
It's
that
better. It's better. Yeah, it's I was getting worried. I was really worried about it for a while, but I think a lot of it has to do with just because I sit so much throughout the day.
Yeah.
And so now I got this like lumbar support for my office chair, and when I'm driving too, you have really bad posture. And so I have
Yeah.
this lumbar support in my car too, and so that's been really helping a lot.
That's good.
Yeah. So at least it's getting better. I was worried that, if it wasn't getting better, then I'd have to, maybe surgery or something like that. But
Jeez.
but the fact that it's getting better means
That's
that,
good. Yeah.
Yeah.
You ever just pop like a deep squat just to like stretch out that area?
a little bit. Yeah. I've been stretching like I kind of lay face down on the ground. And I kind of like
Oh,
like an
cobra
upward-
stretching.
upward dog kind of thing.
Yeah.
Yeah.
Yes.
Anything to like put the spine kind of back in this direction is good.
Yeah.
Yeah, it was on the mend really well. And yesterday I got dinner with a friend,
Mhm.
and we drove around his car a bit, but his car, his seats are like really kind of laid back, and so actually after yesterday I was hurting again just 'cause
She
Like,
was
all right.
spraying it up. I
Yeah.
remember last year when I had that issue, like I just drove with the seat just completely stiff up,
Yeah.
just to like make sure that the pain didn't make me lose control of driving.
Mhm.
Sounds like you're feeling your age, Dr. Tran.
I know. I know. Don't tell me. I was lamenting about it with my friend yesterday too. We had a lot of deep conversations of what it means to be an adult.
Back pain.
Back pain,
Oh.
yeah. Yeah, he's a bit different than me, because like he still feels like he wants to accomplish a lot more in his career too. But then, now that we're kind of past 30, and so I think what he says that, it kind of feels like, we're kind of on a track right now. It's hard to kind of change. And so
Yeah.
Yeah.
Feel that.
I don't. Yeah, that's the big problem. I don't exercise. It's just hard with my schedule, just because because I mean, I mostly teach like evening classes here, just because I just naturally teach a lot of tech electives and grad classes. And so you would think I'd be able to exercise in the morning, but I have because of the parking situation, I have to get here before 8:30 in the morning, because I don't leave today until after 8:30, sometimes even later, depending if I'm meeting with my grad students. And then walking all the way across campus to the other parking structure, because that's the only one that has parking, or sometimes even across the street, like across State College. I don't enjoy doing that at like 8:30 at night when I'm hungry and when I get home. So, and so I just get here really early, but then that just means I'm here for like the entire day, which makes it hard. Oh yeah, yeah. You're more disciplined than I do because I get home and then I eat and I sleep and then I don't wake up until like maybe 6:30 the next morning. So, but then I have to get ready for the day too. So, yeah, this semester was a bit harder just because I have this class and I have the grad class after this, and so yeah, the ones that end at 8:30 are always tough. But that's when the grad classes are.
3 more weeks.
Yep. I don't have a right to complain. You guys have it a lot worse than I do, though, so
You're free to that.
at least I get paid to be here, though. That's the main thing.
That's true. You get one of those walking treadmills for your office?
I
The
could,
flat ones.
but I don't think they would be approved here.
You're so nosy.
It would take a year and a half just to get it approved by like all the bajillion departments here,
Oh
and
my
then
gosh.
yeah. Nice, dang, 30 pounds. That's awesome. Yeah, that's awesome. That's great.
Nice.
All right, it's 5:30, so let's go ahead and get started today. Good evening, everyone. How's everyone feeling? At post midterm, I know that midterm was a doozy. Yeah, so I've been hearing from people. So I haven't started grading them yet. But I probably will start grading them, if not Friday, then probably Monday. And so I'm hoping to get it back to you guys by Monday. Okay. And so, I think this is a good time to just kind of, remind everyone my grading policy. So I don't curve exams in the traditional sense, but what I do adjust grades at the end. And so what I mean by that is that, I try to aim for a certain course average, for everyone's grade at the end. And for a tech elective like this, I like the course average to be about 80% at the minimum. And so if once all the grades are in for all the exams and the projects and everything, and I see that the overall class average is below 80%, so let's say it's like 77%, then what I'll do is I'll add a flat amount of points to everyone's grade. And so in that example, I would add 3 points to everyone's grade, and then your letter grade would be calculated based on that new percentage. Okay. So I don't do it until the end just because I know just lots of things can shake up. Typically projects are scored better than the exams. Just because you have a longer time to work on the projects, and it's I think it's a better culmination of what you've learned. And so I know the exam was scary, and it typically is in this class, that second exam. But we still have the final project, and then we have the grade adjustment after that as well. And so if you're still in kind of a good shape after the exam, and so you're not falling drastically below where you want to be, then I think you still you're still going to be in really good shape. Okay, I also wanted to talk about the plan kind of for the rest of the semester. And so, counting today, we only have 5 more lectures until the end. Okay, so we still have a bit of content to cover. And so I have the lecture notes on higher order schemes. And so I think that'll take us maybe about 50 minutes a day to finish up. And then we have one more set of lecture notes after that, which is unsteady problems in finite volumes. Okay, so that's lecture notes 13. And so I think that'll probably take us 2 lectures to finish up. Right? And so my goal is by next Wednesday, either by the end of next Wednesday or by middle of the lecture next Wednesday, we'll be done with all the content for this class. Okay? And then after that, what my plan is to kind of have just in-class time just for you guys to work on the projects. Okay, because the project it is a fair amount of coding, and so I know we've gotten practice coding through the homeworks, but that's kind of the biggest one that you're going to have to put together all at once for the project. Okay? And incorporates a lot. So incorporates these higher order schemes, and incorporates everything that we've talked about before. So I want to make sure I have time in class for you guys to work on it, for you to ask me questions. Just because I know the office hours are not the most convenient for everyone to meet. And so what ends up happening is that, I end up, meeting with a lot of students individually, and that, becomes really time consuming too. And so, I want to have time in class, because I think that's a nice time when we're all together, when I'm here, you guys are here. And so you guys can ask me questions on the project. Okay? And so that's going to be the plan for at the very least the last week, but maybe a little bit of next week as well. There is one more homework assignment that I want to give out just because, this higher order scheme stuff is a big part of your project. And so I want to make sure you guys get some easier practice with it, before you start implementing in the final project. And so I believe it's going to be homework 6, right? So I think the last one we turned in was homework 5. And so homework 6 will be due on the Friday of the final week. And the idea with that is just for you to get some practice with it. And, after it's due, I'll post the solutions just so that you'll have some references to look at for these, for these high order schemes. I think especially for the quick scheme. So the quick scheme, we started talking about it last time, but in terms of implementation, it can be difficult. And so I want to make sure you guys have, at least a couple examples to look at, a couple examples to practice, before you try implementing that for the project, if you want to do finite volumes for your final project. Okay. Oh, and for the final project as well, I know I still need to make the starter code for finite volume. And so the starter code is out there if you want to do finite difference for the final project. But if you want to do finite volumes, or if you're taking this class for grad credit, then you have to do the finite volume version. I haven't finished the starter code for that too. And so I'm going to work on that tomorrow morning and then get that out to you. So, so you can take a look. And I think now is kind of a good timing for it too, just because, we're finishing up the higher order schemes and we're going to start talking about the unsteadiness in finite volumes as well. Okay, so you can look forward to that starter code probably tomorrow. Okay, so a lot of announcements today. And so are there any questions I can answer about anything about how the class is going to go for the rest of the semester or the exam or anything? Okay, all right, so let's go ahead and get started today then. Okay. And what we were working on last time was the higher order schemes, higher order convection schemes with finite volumes. Okay. Okay. And so just as a refresher, the reason we're kind of embarking on this journey of higher order schemes is that, we've seen kind of repeatedly throughout this class that, whenever we work with the convection term has a lot of issues, right? It has a lot of problems. And so the idea is that if we use a better discretization scheme to deal with convection, a lot of those issues are going to go away. Does somebody have the question? I hear someone's mic is on. Oh. Okay. And so last Wednesday, we went over the higher order scheme for finite differences, which was simply just the 4th order scheme. Okay. And so we talked about that, what that was, and we did an example. And then we left right in the middle of doing the quick scheme for finite volumes, right? So remember, quick is an acronym, and it's not actually fast to do. In fact, it's probably more work to do than anything we've done in this class. But it's a special scheme that is really well designed, to handle convection, right? And so I won't write out the meaning of the acronym again, but I will say what it means. And so quick stands for quadratic upwinding, or quadratic upwinding interpolation for convective kinematics. And so very clever scheme. And so the idea is that, if we have our typical finite volume integral, okay. And so let's say that, we have an east integral here. So remember, finite volumes, we have 4 integrals around all the different cells, all the different sides of the cell, excuse me. And so here's our for example, the east side integral. And so when we apply the trapezoidal rule to this, we end up with the following. Okay. Right. And so we get 2 terms. And so the first term is our convection contribution. And so that phi sub little e right here what this is the value of our solution variable on the east edge. Okay? And so if we have a cell like this, okay. And so here we have phi sub c, right? So remember, phi sub c is the value of the solution at the center of the cell. Then phi sub little e is this one right here, okay? And so normally what we did with finite volumes was we used a simple central difference for this, right? And so if we consider the neighboring cell here, okay, so this phi sub big E, right? So the east neighbor. What we said before was that phi sub little e was just the average between these two. So phi sub c plus phi sub big E divided by 2. Okay, that makes sense because it's right in between. So this right here is our normal central difference scheme. Okay. It's not really a difference, but it's our normal central scheme, but we've used central difference a lot. Okay. But what we've seen before is that this can lead to a lot of issues, and so we had other ways that we can implement this as well. Okay. And in fact, there are two quick schemes, and so there's it depends on which side that you want to put the extra cell. Okay. And so we can improve this. And so we can improve this by adding one extra cell to this approximation. Okay, and so instead of just using two cells, we're going to use 3 instead. Okay, but because we're only adding one cell, there's a choice of whether you add that extra cell to the left or if you add that extra cell to the right. Okay. And so this gives rise to our 2 schemes. Okay. And so I think last time I labeled them quick 1 and quick 2, but but you can kind of label them what you want. And so maybe one better way is just one's on the left, one's on the right. Okay. Okay. So one scheme adds the extra cell to the left. Okay. Or maybe a better way to say this, on the opposite side of the edge value. Okay. Because this edge value here is on the east edge of the cell, right? And so if we add phi sub w here, okay, we're adding that extra cell on the opposite side. Okay. And so under this approximation, we have phi sub little e is equal to minus 1/8 phi sub w. Okay, so that's the extra cell plus 3/4 phi sub c plus 3/8 phi sub big E. Okay. Or we can put the extra cell on the same side as the edge value. Okay. So we have here is phi sub E is equal to 3/8 phi sub c plus 3/4 phi sub big E. Okay. And in here comes our extra cell. So we have a minus 1/8 B sub 2e. Okay, and so the 2e indicates the fact that it's going to be our neighbor's neighbor on the right-hand side. Okay. Okay, so that's kind of where it would be located relative to the other ones. Okay. Okay. And so naturally, what we expect that by adding an extra cell or adding an extra variable here, this is going to be a more accurate representation of our convection term. Okay. But then that raises the question, right? So if we have two different versions here, how do we choose which way or the other, right? And so, it's more complicated than just flipping a coin or just choosing the one you like better. Okay. And so the way that we're going to choose between these two versions depends on the direction of the velocity. Okay? And there will be a velocity if you're using this, because remember, if you have convection, then naturally you just have velocity. And remember, typically what we do is that, whenever we have a velocity, we like to put extra weight on the upstream side of that velocity. Okay. Because that's where the information is coming from, and that's that's going to lead to more stable solutions. Okay. Okay. And so I'm going to do a 2D example here, and I'm going to show you what each of the four integrals look like under the different conditions. Okay. All right. So a little bit of a lengthy recap, but I know it's been a while since we've seen this stuff, and so I want to make sure that we're all kind of starting out on a good page. Okay. So any questions on this? Okay. All right. So let's go ahead and do an example here. I call it an example, but it's really just kind of working out for all this stuff. Okay. And so let's apply quick to a typical finite volume integral in 2D. Okay. And so this means we're going to have four integrals here. Okay. And each of those four integrals are going to branch off into two different paths. Okay. So we're going to have 8. Although technically, if you include the default case, we're going to have 12 different cases here. So it's a lot of writing, but I want to make sure you guys have all of it, just so that because we're going to look at this in the code, and so I want you to have this reference here to kind of see where I got all these terms, all the coefficients, and all the signs and things like that. Okay. Okay, so let's go ahead and formalize the one that we just did, which is the east integral. Okay. And so when we perform trapezoidal rule for the east integral, we have delta y times b sub little e times u minus k partial phi partial x on the east edge. Okay. And so this is going to have two different versions here. Okay. Okay. And so let's do the one when the velocity is positive. Okay. And then we're going to have one where the velocity is negative. Okay. And so if the velocity is positive, that means the velocity is coming from left to right, right? So it's going from the left side to the right side. And so that means the extra cell that we want to put is going to be on that left side, right? And so what we have here is that we have u delta y times, and we're going to use version 1 up here, right? So version 1 is going to be a minus 1/8 b sub w, right? Because that's where we want to put the extra cell on the west side. Okay. Okay, plus 3/4 v sub c plus 3/8 v sub big E. Okay. Minus. And then we have our diffusion term. And so our diffusion term is not going to change. And so that's going to be the same. The delta y here too. Okay. Okay. So when our velocity is positive, we put the extra cell on the left, which is why we have phi sub w here. On the contrary, when the velocity is negative, that means our velocity is coming from right and going left. And so the extra cell that we want to put is going to be on the right. Okay. So we have a u delta y. Okay. Then we have a 3/8 v sub c plus. Okay, and so this is version 2 of what we have above. So 3/4 v sub e minus 1/8 v sub 2e. Okay. And of course, we have our diffusion term as well. So we have minus k v sub e minus v sub c divided by delta x delta y. And so you're going to choose between these two. All right, so that's the yeast integral. But of course, there's also a hidden third case. I guess it's not that hidden, but whenever we're adding extra cells like this, kind of the assumption, kind of the stipulation is that we can actually put those cells there to begin with in the first place, right? And so it might so happen that we might not have a neighbor on the west side, or we might not have a neighbor, to east of us, okay? And so if we run into a situation where we don't have enough neighbors to accomplish the correct quick scheme, then we have to default to something. And so the default that we typically do just for the sake of simplicity is just simple central difference. Okay? And so, of course, you can take this base case here and make a version with positive velocity, negative velocity. But for the sake of simplicity, we're just gonna have one base case, okay? And so we're gonna ignore upwinding, and so we're just gonna have just our usual central difference. Okay? So we're gonna have u delta y times phi sub e plus phi sub c divided by 2 minus k phi sub e minus phi sub c divided by delta x delta y. Okay. And so for our convection phi value, we just use our standard central difference for that. Okay. Any questions on this? Okay. All right, that's the yeast integral. So now let's look at another one. And so let's look at the south one. All right, so the south integral, after we perform trapezoidal rule, we have this. Since we have delta x times minus phi sub s times v plus k partial phi partial y on the south edge. Okay. All right. This one's interesting because the sign convention is changing, and the edge is actually on the bottom face as well. Okay, so what we interpret to be, opposite side and same side is going to be a little bit different here. And of course, we're going to have two cases here. And so if we have the case with v is greater than 0, okay, so v is going from bottom to top, and we have a case where v is less than 0 as well. Okay. And so let's do v greater than 0 first. And so when v is greater than 0, that means the velocity is coming from bottom to top. And so the extra cell that we want to put is on the south side. Okay. But you have to be careful here because, you have to think about, what's on the same side versus the opposite side. Okay? Because it's very tempting to just, now that we did the east face, is just to kind of copy that same convention over to the south. But the south face is a little bit different because it's on the south face, and the velocity is going from up and down. Okay, and so the version that we're actually going to use here is actually going to be version 2. Okay, and once I write it down, then you'll see why. And so for v is greater than 0, we have a minus v delta x times, we have a 3/8 v sub c plus 3/4 v sub big S minus 1/8 v sub 2s. Okay. And then we have our diffusion terms. We have a plus k v sub c minus v sub s divided by delta y times delta x. Okay. All right. And so we use version 2 here, right? So go ahead and draw it for you. Okay. Right, and so if here's our cell, and our bottom maybe here is phi sub s, right? Remember, we're approximating the value of the edge value right here, okay? And so if our velocity is going this way, right? So in other words, if v is positive, that means the extra cell that we want to add is going to be on the bottom, right? And so what's more bottom than phi sub s? It's phi sub 2s. Okay. Okay. And so that's why we use kind of version 2 up there. And so that's why today I wanted to change that notation instead of quick 1, quick 2, which I think is how I labeled it last time. I want to label in terms of the one that has the closer side, the one that has the farther side. Okay, opposite side, same side. Because I think that makes more sense within the context of finite volumes anyway. Okay, so that's when v is greater than 0, and when v is less than 0, then we're going to use the other scheme here. So we have minus v delta x times. The opposite side is going to be the north, and so we have a minus 1/8 p north plus 3/4 p sub c plus 3/8 p sub s, okay, plus k phi sub c minus phi sub s divided by delta y phi sub x. Okay. Okay. And of course, we have our default case. And so if we don't have enough neighbors, then we just default to just simple central difference. Okay. We have minus v delta x times the average phi sub c plus phi sub s divided by 2 plus k phi sub c minus phi sub s all divided by delta y delta x. Okay. So that's our plan for the south integral. Okay. Okay. And so hopefully, when we take it kind of slowly, kind of integral by integral, it makes sense kind of why we choose one scheme or the other. But as you can see, this takes a lot more thought. This takes kind of a lot more effort than our methods from the past, right? Because in the past, at most that we would have to think of, what's the upwinding side, and we just choose the upwinding scheme because of that. But now we have to make kind of multiple decisions. And so we have to choose, which direction the velocity is going, to check, if we have enough neighbors at all, right? And so there's lots of different decisions that you kind of have to make. Okay. When you're making these decisions by hand, with the human brain, it can be overwhelming because it's a lot to check at once. But with the computer program, you can think of each decision that you have to make, each choice, that just becomes an if statement. Okay. And so that's why you see a lot of these methods kind of explain in this kind of way, because they're designed to be computer algorithms with if statements and for loops and things like that. Okay. So each decision that we have to make it's just a different if, right? And I even wrote it here too. So, if, right? So whenever you say if, that's going to be an if statement. Okay, so that's the south integral. So now let's do the west. Okay. And so for the west integral, we have delta y times minus e sub little w times u plus k partial phi partial x on the west side. Okay. Right, and we're gonna have two cases here as well. And so we have u is greater than 0, u less than 0. Okay. And that's going to correspond to our two quick schemes. All right, I'm going to go a little bit faster here just because it's kind of more the same thing. Okay. And so if our velocity is greater than 0, that means we want to put the extra cell on the west side, on the left. Okay. So that means we're going to have phi 2w. Okay. So we have a minus u delta y times minus 1/8 phi 2w plus 3/4 p sub w plus 3/8 p sub c. And then we're going to have a plus k p sub c minus p sub w divided by delta x delta y. Okay. And then for phi less than, and for u less than 0, we have the opposite. So we have a minus u delta y. We're going to add the extra cell on the other side. So we have a minus 1/8. Other side of west is east, and so we have phi e minus 1/8 plus 3/4 p sub c plus 3/8 p sub w plus k p sub c minus p sub w all divided by delta x delta y. Okay. And if not enough neighbors, if we don't have enough neighbors, we just default to our usual central difference. So we have minus u delta y p sub w plus phi sub c all divided by 2 plus k phi sub c minus phi sub w delta x delta y. Okay. All right. So that's everything on the west. Okay. So if anything, the west actually resembles more closely the south side because it's on kind of the, west and south kind of go together, just like the airline, and then north and east also kind of go together, like the university. That's how I like to think about it. Okay, and so the last one we have is the north one. Okay. And so we have delta x positive phi sub n times v minus k partial phi partial y on the north side. Okay. And we have two forms here. V greater than 0 and v less than 0. Okay. And so for v greater than 0, we're going to put the extra cell on the south side. And so we're going to have a v delta x the extra cell always gets the coefficient of minus 1/8. Okay, so we have minus 1/8. The opposite side here is on the south. Okay. And then we have the version when v is less than 0. Okay, so we have v delta x minus 1/8. Here, the side we want to go extra on is the north side. So we have phi 2n plus 3/4 phi n plus 3/8 phi sub c plus. I'm sorry, these should be minus k's, not plus k's. Minus k, minus k. Minus k, phi sub big N minus phi sub c delta y delta x. Okay. And of course, if not enough neighbors, then we have v delta x, their default scheme phi sub n plus phi sub c divided by 2 minus k phi sub n minus phi sub c all divided by delta delta y delta x. Okay. Let me zoom out just so you can see kind of all 4 of them in their glory. Okay.
For the v less than 0, is that supposed to be a 3/8 for the phi sub c, or is that a 5?
Oh, it's a 3/8.
Okay.
Yeah. Yeah, thanks. Yeah. All right, it was so much that it all didn't fit in one screen. So I could zoom out a bit more, but I think it would make it unreadable. And so, you know, it's a lot. And so, and you know, we're going to go over the MATLAB example in just a second. And so, you know, it's a lot of MATLAB code too. So I think it's going to be the most impressive MATLAB code you've probably seen, you know, in the class so far, until you do your projects. And so your projects will be even more impressive than this.
So the format is always -1/8, 3/4, and 3/8.
Exactly. Yeah. Yeah. It's always going to be those 3. It's just, you know, how you arrange those around depends on what direction the velocity is going. And so the -1/8, that's always going to be your extra cell, you know, whichever side you put it on. 3/4 is actually used on the neighbor that's closest to the extra cell. And then the 3/8 is just the one that's farthest away from the extra cell. That's kind of how I kind of envisioned in my mind as well. All right. And so make sure you have all this written down, because, you know, when we look at the code, you know, you're going to see all these things in the code, but as, you know, as if statements and as code. Okay. So before we do that, are there any questions on this? Okay. Okay. And so the way the code's broken down, is that, you know, if you kind of remember our code that we looked at for finite volumes convection, you know, I had basically different blocks of the code to correspond to the different integrals. Okay. And it's going to use that same style here. Okay. Okay. And so within the for loop, we're gonna have 4 different blocks of code. Okay. And each of the blocks of code are going to implement, you know, the method that we have up there. Okay. But, you know, before we looked at it, because it's going to be a mess of if statements and else statements and things like that. I want to kind of run you through the logic of what each block of code is going to check. Okay. All right, so actually there are actually 5 checks that it has to do overall, believe it or not. All right, so the first check that we have to do is we have to check to see if we're on a boundary condition or not, right? So we can't forget about boundary conditions throughout all these things. Okay? And so if the edge sits on a boundary condition, then we kind of abandon all other plans and we just apply the boundary condition. Okay, so that's the same as we have been doing. Okay, so that you don't apply any higher order scheme for that as well at all. Okay. 2. All right, and so if we get past that first check, then we know that we're not on a boundary condition. Okay, and so the next check is we have to check and see which direction the velocity is going to go. Okay, and so I'm going to use U here as an example, but the same thing applies for V as well. Okay. Okay, and so first we're going to check and see if our velocity is greater than 0. Okay, because that tells us which scheme that we want to use. We also need to check to see if we have enough neighbors to execute the quick scheme. Okay. And so that's 2 things we're going to check. We're going to check to see if the velocity is positive, and we're going to check and see if we have enough neighbors. Okay. And so if that's true, that means we apply the appropriate quick scheme. Okay. Okay. I say the appropriate quick scheme because it depends on which side of the cell that you're on and where the extra cell is going to go. Okay, but we kind of just spent the last 20 minutes talking about what the appropriate one is for each situation. Okay, third. And so third is also going to be a case when the velocity is greater than 0. Okay. But let's say that we don't have enough neighbors. Okay? Right, and so we know that we know the direction of the velocity, right? We may not be on a boundary, but we actually don't have enough neighbors to execute the quick scheme. Okay, so these cases are rare, and so they don't appear all the time, but we do have to account for them. And so in these situations, just like we did above, we apply our normal central scheme. Okay? All right, so cases 4 and 5 are kind of the mirror images of 2 and 3, except when the velocity is negative. Okay, and so for 4, U is going to be less than 0, and let's say we have enough neighbors. Okay, and so we're going to apply the appropriate quick scheme. Right, if you did everything right, the quick scheme that you apply in the fourth case here is going to be the opposite one in step 2. Right, so step 2 and step 4 should not be the same. Right, so they should be opposite quick schemes. And the fifth case, we have U less than 0, but then we don't have enough neighbors, and so there we just apply our normal central scheme. Okay. And so that's the logic that each block is going to go through. And so, now we're going to see how this is actually implemented in code. I did want to go through that, because it is quite a lot of logic. And so, I'll as we're going through the code, I'll point out each of these 5 different cases for you, so you can see, how it's implemented. Right? Because it's not as straightforward as, case 1, case 2, case 3. There's if statements, else statements, and nested if statements and things like that. But these are essentially our five use cases, and I'll point them out to you as we look at the code. Okay. Any questions on this before we jump to the code? Okay. All right. So let's go ahead and jump to the code, just so you can kind of see. Okay. So let me go ahead and share screen. Okay. Oh, that is way too small. Okay, let's drag this to a new window. Okay, so here's the code. So I posted this onto Canvas, and so you guys have this exact code as well. Okay. Okay. And so let's go through this code, right? And so our front section here, our section 1, that's all the same, and so we don't change that at all. Okay. All right, so let's jump into the for loop, because this is kind of where everything, all the magic happens, right? And so first thing you see here is that we are computing the ID numbers for phi sub c and all its neighbors, right? So this is fairly standard, right? And so all our 2D codes have this. And so what's new here is that we also compute the ID numbers for all the distant neighbors, right? So we have west ID 2, east ID 2, north ID 2, south ID 2. Okay. We may not need all of them, because we may not require their services depending on the direction of the velocity, but it's good to compute them, right? Just to make sure that they're available, right? And so I've labeled them with a comment here about what each of these ID numbers represent. Okay. And you can derive their values, just the same as from here. It's just you add either an extra 1 or subtract an extra 1 from I or j. Okay, and so now we enter the magic. Okay, and so this entire block right here, this is just for the east integral, and so this is probably the biggest block of code that you have just for one thing that we've seen in this class. Okay, well, let's kind of break it down just kind of step by step here. Okay? All right, so the first thing we check, and so remember this is the east integral here, and so for a typical cell, right, this is going to be for this edge right here. Okay. Okay, so the first thing we have to check and see, if our cell boundary borders the domain boundary. Okay, and so if this cell is on the very right side of the domain, and so that's what this if statement is checking right here, right? And so if I, okay, remember we have I and j, so I and j denote what position our cells are in. If I is equal to nx, that means we're on the very rightmost side of the domain. Okay, and so if that's the case, we're going to apply our boundary condition. And in this case, for this problem, I should have written out the problem, but for this particular problem, it's a Dirichlet boundary condition. Okay, and so that's what we're doing here. And so this is nothing new. And so we've done this before with our with our previous codes. Okay, and so that's kind of case 1 from our kind of our breakdown just now. Okay. All right, and so now we get to the fun part. And so this is when things, really different. Okay. First thing we're going to check, and so if we're not at the boundary, and so if this thing returns false, then we proceed with the if statement that's on the same line as that. And so if you notice how this if, else if, and else, they're all vertically aligned, right? So that means all 3 of these are matched up together. Okay, and so if this if statement fails, and so if we're not on boundary, then the next place we go is here, okay? Because it's on the same, it has the same, horizontal spacing as the first if statement, okay? And so first we're going to check and see if the velocity is positive, okay? And so for velocity is positive, that means it goes from west to east, okay? And so if that's true, then we go into here where we check and see if we have enough neighbors, okay? And so the first thing we check here, so, in order for us to have enough neighbors, okay, if the velocity is going from west to east, that means the extra cell that we're going to put in is going to be on the west side. Okay. That means that, we have to have an extra cell on this side of our cell here. Okay. And so the extra cell would just be the west, would just be straight up the west neighbor, okay? Because we're looking at the east edge, and so the extra cell would be on the west. Okay? Because normally, if we're taking this edge, we just take phi sub c and phi sub e. Okay? And so if we had an extra one, it would be phi sub w. Okay. And so in other words, we need to make sure that we have a west neighbor, in order for us to apply quick. Okay. Right. And so another way, I know this comment here is generic, but let me go ahead and make this comment a bit more specific. Okay. And so if I is greater than 1, right? And so if our x index here is greater than 1, that means we must have a west neighbor. Okay? Because the only cells that don't have a west neighbor have I is equal to 1. Okay? And so we look at our typical domain here, right? So here's our typical domain, yada yada yada. Okay. It's really bad, but I'm drawing with a mouse. Okay. And so, the only cells where we wouldn't be able to apply this quick scheme on the east integral would be all of these right here, right? Because all of these cells here, they don't have a neighbor on the west, right? And so what all of these cells here have in common is that their I index, okay, which denotes, their position in terms of x, all the I indices for this column of cells right here are equal to 1, okay? And so if we check and make sure if I is greater than 1, that means we must have a west neighbor guaranteed. Okay. Okay, and so if we have our west neighbor, then we can go ahead and apply our quick scheme as we know it. Okay. And so you can see here we have A my ID west ID, A my ID west ID. Okay. And so we're going to apply the coefficient here. And so since this is the extra cell, we have a minus 1/8. Okay. Minus 1/8 times u times dy. And then we add the other coefficients, right? And so we have my ID, and so this is phi sub c, as you can see from the comment here. And so this has a coefficient of 3/4 times u times dy, okay? And then we have a coefficient of k as well, okay? So this comes from the diffusion. And so don't forget about diffusion. And so diffusion is there as well. And so I think the tendency for the quick scheme is to focus completely on the convection, but we can't forget about diffusion as well. And then finally, we have the coefficient for east ID. So we have my ID east ID, my ID east ID. And then we have the quick coefficient for this, which is just a 3/8 times u times delta y. Okay. And so this entire block of code right here, this is case number 2 of the breakdown that we just mentioned. Okay. Okay. And so does all this kind of make sense so far about all the checks that we've done and the reason we chose this scheme, this quick scheme so far? Okay. All right. Okay. And so that's if we have enough neighbors. If we don't have enough neighbors, right? And so if I is equal to 1, right, then we enter into this loop. And so this part right here means that we don't have enough neighbors for the quick scheme. And so we just use our basic central scheme, right? And so here we kind of default to what we've done before. And so we have my ID, which is phi sub c. That's u dy divided by 2 plus k. And then my ID east ID, we have plus u dy divided by 2 minus k. Okay, so this is just kind of our basic scheme. And so these 2 lines of code here would be case number 3 of the breakdown we just did. Okay. Okay. All right, and so that's everything that we need, to take care of if the velocity is positive. Finally, we're going to look at the case when the velocity is negative, and so we're going from east to west. Okay, and so if we're going from east to west, then our extra cell is going to go on the east side. Let's see how that's implemented. Okay, first we need to check and see if we have enough neighbors. Okay. And so the condition here is that we have to have a neighbor that's 2 east of us, right? And so here phi 2e has to exist, okay? And the way that we check to see if phi 2e exists is we check to make sure, that we are, that our I value is less than nx minus 1. Okay. Let me just go ahead and draw the domain again really quick. Okay. And so those are the last three columns of our domain, right? And so in the last column, we have I is equal to nx, okay? That's a situation we've already dealt with, because if I is equal to nx, then we apply the boundary condition on that side, right? So that's when we have the eastmost cell, okay? If we go one left of that, then our I value here is going to be nx minus 1. Okay? And so that corresponds to this column right here, right? And so we just moved one over on x, and so our I is 1 less than that. Okay? In order to apply our quick scheme, we actually need to be in this column, at the very least in this column right here, or anything to the left of this. Okay, and so this column right here has a value of I is equal to nx minus 2. Okay, and so one way that we can incorporate this in the code is we can say that if I is less than nx minus 1, then we have to be in this nx minus 2 column at the very least. Okay, we might be somewhere to the left of that, but we are at the very least right here. Okay. Okay. And so another way, of course, another way that we can incorporate this, of course, is that instead of less than, we can have less than or equal to. Okay, and this might make a bit more sense. And so if we use less than or equal to, this would be nx minus 2 instead. Okay, that means we have to be at least nx minus 2, or we can be less than that. Okay? But just to make it more elegant, I like to just use less than sign. So that's why I have it as I is less than nx minus 1. But you can also do less than or equal to nx minus 2 as well. Okay, and so if this is the case, then we have enough neighbors for this, and so we just go ahead and apply the scheme. First, we have our extra cell, and so since our extra cell here is 2e, then we're going to have our extra coefficient of minus 1/8 u dy, and then we have phi sub c, which has the coefficient of 3/8, plus k, which comes from diffusion, and then we have our coefficient of phi sub e, which is 3/4 u dy minus k. Okay. And so these three lines of code right here, I guess 4, if you include the if statement, this is case number 4 in the breakdown that we just did. Okay. And then finally, if we don't have enough neighbors, and so if we're in this column of cells right here in particular, then we just use the central scheme. Okay, so that's u dy divided by 2, u dy divided by 2 for phi sub e and phi sub c. Okay. And so that kind of breaks down, how I kind of structured this code and how you kind of see each of the different, cases that we went over. Right? Any questions on this? Okay. All right. So I'm not going to go over the other integrals because they all kind of follow the same logic, but I think it's kind of a good exercise for you guys to do as well. And so, when you're doing the homework and you're working on the quick scheme, look back on this example to see how each of these were implemented. Okay, and so you can see here I have a block for the south integral, a block for the west integral, a block for the north one, and so on and so forth. Okay, and then after that you could solve. And so let me go ahead and run the code. So it took about 1 second, but even more just to produce the plot. Okay, and so here's what we get. And so I think this problem here was a repeat of the convection finite volumes problem that we did before, except now I incorporated the quick scheme. Okay, and so for this problem, we didn't really have any issues with stability or with upwinding, and so we end up getting the exact same solution as before. Okay. All right, and so that's high order schemes, and so that's a big part of your project. I will say that one thing that I'm kind of intentionally not doing together in the class is combining a higher order scheme together with an unsteady scheme. Okay, and so that's going to be kind of the big kind of theoretical jump that you guys are going to have to make for your project. And so combining kind of what we just did together with like an implicit Euler to get time marching scheme from that. Okay, and so next we're going to go over how we do unsteady schemes with finite volumes in general, but I'm not going to do it with a higher order scheme. So that's going to be part of your guys' projects. Okay, so let me go back to the iPad here. And for the last 15 minutes today, we're going to talk about, finite volume schemes for unsteady problems. Oops. Our question. So for grads, so both FDM and FEM need to be done, or just FEM? You need to do both. And so if you're a grad student or taking for grad credit, you need to do both FDM and FEM. Yeah. All right. And so our journey is nearing its conclusion. And so, you can see that, we've taken basically the same journey, through finite volumes as we did with finite difference. Okay. And so if you remember, and so a lot of you do remember this because it was just on the midterm, right? But the last topic that we went over for finite differences was how to cover unsteady problems. Okay. And so now we've kind of finally arrived at the same point for finite volumes. And so remember, the big difference with unsteady problems is that now we're dealing with the time derivative, right? Partial phi, partial t. Okay. Right. Luckily for finite volumes, finite volumes actually doesn't do anything too differently. And so for finite volumes, we're gonna discretize this in the exact same way. And so we're gonna have phi n plus 1 minus phi n divided by delta t. Okay. And we have the spatial coordinate as well. And so we have, in 1D, we just have phi I, phi I. Okay. And so we do this in the same way as finite difference. Okay. And so actually, everything that you learned before with explicit Euler, implicit Euler, that's going to apply here as well. Okay. The only difference with finite volumes is that all the other terms, all the diffusion, the convection, the source, those will be discretized differently. Okay. But the unsteady term will be discretized the same as before. Okay. Okay. All right. And so, because we're doing finite volumes, we're going to have the concept of the integrals, right? And so our integrals are make an appearance, and we're going to do all those the same way, except now we're just going to add this extra term in there as well. Okay. But one thing that we will have to take into account is the fact that, remember, the way that we obtained our finite volume equations was we performed an integral over our entire conservation equation. Okay. And so that's going to be the same thing with our unsteady term as well. Okay. Okay. And so, when you write out the equations, you might have a term that looks like this. Okay, so we'll do the 1D first, as we're gonna have integral of partial phi partial t dx. Okay. The good thing about this is that, our derivative here is in time. Okay. But when we perform this integral is over space, right? So that's why we have dx. And so when we actually evaluate this, okay, those two things are actually going to be separate. And so for the time derivative, we're going to discretize it just like we saw above. Okay, so we have phi n plus 1, phi n at I, okay, divided by delta t, okay. Actually, let me change these. And so, instead of I, right, since we're doing finite volumes, we don't use I, we use C, right? It's a little change, but remember, these are the self-centered values. Okay, so it's phi sub C n plus 1 minus phi sub C n. Okay. And then we're going to multiply this by the length of the cell, okay, delta x. And so in a way, you can think of this as, we're treating this time derivative term exactly the same as our source term. Okay. Okay. And so the way that we obtained that expression was that, we just applied trapezoidal rule straight up on that term. Okay. Okay. And so that's where the delta x comes from, and that's where the phi sub c comes from as well. Okay. So remember trapezoidal rule, if we have an integral, we evaluate the integrand at the centroid of the domain, and so that's phi sub c, and then we multiply by the length of that cell. Okay. And so this is in 1D. We have a 2D version as well. Okay. And so in 2D, what we have here is phi sub c n plus 1 minus phi sub c n over delta t. Okay. And so just like before, we're evaluating phi here at the centroid of the cell, right? Phi sub c. But instead of multiplying by length, we're multiplying by the area of the cell. And so it's going to be multiplied by delta x, delta y. Okay, so this delta x, delta y, this is area of the cell. Okay. And so this is our 2D case. Okay. All right. And so the way we're going to do this is, we're going to take our finite volume problems, we're going to discretize it in space, kind of literally the exact same way as before, except now we're going to add some time dependence here, depending on whether we do explicit or whether we do implicit. Okay, so we're going to go through explicit first, and then we're going to see the implicit method from there. Okay. All right. Any questions on this so far? Okay. All right. So let's look at explicit time marching first. Okay. All right. So recall, for explicit time marching, the kind of the hallmark of this is that all of the phi variables outside of the time derivative, we're going to evaluate that at the current time step. Okay. Okay. And since the current time step values are known, then we move those over to the right-hand side of the equation. Okay. And so each equation, right? And so we're going to get one equation per cell, right? Each equation for each cell is going to have just one n+1 term, okay? And that single n+1 term is going to come directly from the time trigger. Okay. All right. And so, I think, this is all stuff we've kind of done before. And so I think the best thing to do is just to jump right into an example. Okay. And so let's do an unsteady diffusion equation. Okay. I don't think we'll have time to finish it, but I do want to start it. Okay. So we have partial phi partial t is equal to 3 partial squared phi partial x squared. Okay. And so we have boundary conditions. And so we have phi of 0 is equal to cosine of pi t. And we have d phi dx. d phi dx at x is equal to 1 is equal to cosine of pi t divided by 2. And so we have unsteady boundary conditions here. Okay. And our initial condition is that phi at t is equal to 0 is equal to 0. And so we just have a 0 initial condition all throughout the domain. Okay. Okay. And so let's go ahead and start the derivation of this. Okay. And so for the finite volume method, remember what we're going to do is we're going to integrate this equation. Okay. And so we're going to have integral of partial phi partial t is equal to dx is equal to 3 integral of partial squared phi partial x squared dx. Okay. And so if we perform this integral and we plug in for partial phi partial t, and so on the left hand side, we're just going to plug in our expression from up here. Okay. And so we're going to have phi sub c n+1 minus phi sub c at n divided by delta t. That's equal to 3. Okay. Before we apply and so here we actually don't need to do trapezoidal rule. Okay. And so what we do instead is that we we just integrate this guy, right? And so since we have a dx there, we're going to have a partial phi partial x. Okay, it's going to be evaluated on the east Or I guess we're in 1D. I should use right and left. Okay. Right minus partial phi partial x on the left side. Okay. And then for these, we're going to plug in our usual linear interpolation. Okay. And so with partial phi partial x on the right, we have phi sub c, or excuse me, phi sub r minus phi sub c divided by delta x. And this one we have phi sub c minus phi sub l over delta x. Okay. And then according to the explicit Euler scheme, we're going to evaluate all of these at time step n. Okay.
We're starting off with explicit.
Yeah, we're starting off with explicit. Yeah. Yeah, we'll do explicit first, and we'll just do 1D. And then the example that I have after that is implicit 2D, because that's more consistent with your project. Okay, and so we're out of time today, and so we'll continue working on this next week. Okay, but that's the general idea. And so it's kind of, there's nothing really new in this last set of lecture notes. It's just kind of an application of a lot of what we've learned before in other weeks. Okay. Have any final questions on this before we wrap it up for the week? Okay, all right, so that's all we got time for. And so we'll continue this on Monday. And so I think I'm pretty confident we can finish this last set of lecture notes by Wednesday. And then from there, we'll just have time in class to work on the project. Right? And so, starting, once we finish this, if you want to have help on your project, I think the best thing to do would be to come to class, just because it's a lot easier for me to kind of help you out with MATLAB when I could be there with you. But I will still help people on Zoom. It's just that, I kind of cycle through the class kind of first. But, we'll talk about that more next week. All right, so thank you everyone for coming today. Hope you guys enjoy your weekend, and I'll see you guys next week.
That's right.
See you guys. Have a good weekend.
I was looking through this solution and we crossed this out already.
Yeah.
And I was thinking here you would reduce it, right? Finding the R total.
Yes, yeah. So the reason I cross this out is because if you don't have a capacitor here, normally capacitors are connected to ground. And so it's not connected to ground, it becomes a lot more difficult to work. And so that's why I kind of crossed it out. And so I kind of made that mistake before where I had that. But for the exam, yeah, because the way we define capacitor is so that the other side is connected to the ground, and so you just do flow in minus. Aaron, any final questions, Aaron? Okay, all right, so I'm gonna go ahead and sign off. I have to give an exam now, so I'll see you next week.